Thank you for coming. My name is Laurent, and I work in supply chain security at Docker. I've been working in DOI at Docker for just over a year, but I've been involved in the DOI ecosystem for since at least 2016. So we hear often in the news about product recalls, very often in sensational matters. The thing to remember about product recall is they're designed to keep defective product, dangerous products out of the hands of customers. Some common ones that we might think about are, for example, exploding batteries in some products that made the news a while ago. And a personal example of mine is one of my previous car was actually recalled because it was attracting certain kind of spiders that would get into the fuel lines, create spider webs, and create damage to the engine. I think that pretty well illustrates the fact that defective product is not necessarily something malicious, it's not something that's necessarily negligent. You just don't know until products is used by user what kind of weird behavior would emerge from this. So these are examples of simple recalls, and there was another one recently where a software company recalled its line of zero sugar drinks because it was in fact full sugar. Not super dangerous, but it still does affect the customers. These are fairly simple examples of recalls, but there are some that are much more complex. My first example is in 2009, there was a salmonella contamination in a peanut butter factory. And this was not just peanut butter that you buy from the jar, this was peanut butter that ended up in other product. Some of these included school lunches and FEMA emergency meals. So this is like recalling a product of this nature is a lot more complicated because they've been spread out to more places. And that at a time was the most expensive recall in the history of the US. And then it was eclipsed just a few years later by the most expensive in history, the recall that was the most expensive, and that's the Takata airbag recall. And what happened in this specific recall is that it would the airbag would trap humidity, it would cause some rust to happen in the injector of the airbag, and when the airbag would deploy, it would also send shrapnels of metal into the user. It doesn't get much worse than this in terms of recall as far as product go, but what made this way worse is that it affected 100 million cars in 100 million units in 37 million cars, but in 19 different automakers. So this product had made, it was widely available, and that caused a pretty big impact. So it is considered to be the most expensive recall in history, and it still hasn't finished. There's still car in circulation that is estimated that are in circulation today that have not been put out of circulation, and the tally for that is 24 billion. In 2021 and 2022, there was over 1 billion unit recalled each of these years. That's a lot of product that are recalled. One of the things too is it sounds expensive. Recalling 1 billion units that sounds like a big problem. It sounds like a very big burden on industry. And while that might be true, not recalling a product that's defective is even worse. Because in 2023, there's $4.4 billion in liability payment from insurance about defective product. And that's just a liability claim. It doesn't factor in the reputational damage and all the other loss of revenue that were involved in dealing with the situation of not having recalled the product in time. So with a problem of this magnitude, how do we manage a problem like this? And this is where this is kind of connected to what we're doing, because you've heard a lot about the supply chain. So the supply chain is something that also applies to physical product, and understanding the physical world might help us understand how this applies to software as well, because in basic terms, supply management is the system of procuring raw materials, components that is developed in a finished product. So the notion of software supply chain is not that far off. And then just like in physical world, well, like in software, we have it's the same. We have supply management, and the tool that they use in physical world is a very similar tool that we use in the software world, and that is the bill of material. The bill of material is a list of raw materials, sub-assembly, intermediate assemblies, some components, parts, and the quantities that makes a product, and that is very detailed. And it's this bill of material in our example, for example, of physical product that allow an automaker to create a service where you can input your VIN, your vehicle identification number, to determine if your car was affected by that specific Takeda recall or any other recall. It would be very, very difficult to do this without a bill of material. It would be next to impossible to do it on a web service that is immediately available. So what does software have in common with airbags and peanut butter? Like why is it relevant that we're using the same tool? And the answer for this is complexity. The mechanism that we acquire these components, stuff like that, might be different, but the way we manage it would be very similar. So that's why we use the software bill of material, which serves the same purpose. One could argue, though, that the software world has additional complexity, because in the physical world, you're limited to the assembly line. How often can you create these batches of product? In the software world, you can pump out multiple versions a day. You can change your dependency on the fly. This moves much more quickly in a software world. And then, in the software bill of material, the part that one of the parts that's most important to security that doesn't get talked enough is the versioning. There's a lot of talk in versioning in software, the importance of versioning to not create breaking change, to not disrupt the developers, but it plays just as much of a role, if not more, to security. The version is the primary mechanism when a tool like Docker Scout or Sift or Trivy, or all like the tools that we heard so far, are able to identify security vulnerability and give you information if a software update is available to fix that vulnerability. Without version information, none of this is possible. So there was a question earlier yesterday, is like, how is this different than a package file that we already know? The answer is complex. Like, first of all, when we talk about a container, it's much more than just one software. It's the entire execution context. So it's the OS that has its own packages. It's all the dependencies. And many times, those softwares are compiled, and those software have dependencies that have to be accounted to. So the SBOM is not solving just the problem of the immediate, but it's trying to drill down. And an SBOM in one package can be picked up in the SBOM in the other and propagate this data through the chain. One of my favorite ecosystem for this is the Go language, because they made a very clever decision of when you compile a Go binary, it bundles the list of dependencies that were used in the actual compiled binary and puts it in the metadata, which means that when you are using a Go binary and it gets scanned, your SBOM is going to include the list of the dependencies that are used with the version. And that's very, very helpful. So if there's a vulnerability in the package, not only the high level or the very popular application that uses it is going to get a vulnerability notification, any other software that uses it is going to get it as well. Where it gets less good is that we've all done it. There's a fix, a new feature that exists in a dependency that we're using, and it's just not coming fast enough. Like, they're promised that they'll do a version in a week, maybe a month. We want it now. So what we do is we create a monkey patch, or we go directly link to the Git commit. And what happens in this case is there's ways to do it properly, but more often than not, this information is lost, which means that you end up with a SBOM like this, where the version information is useless. So if this identifier actually maps to a version that has a CVE, the user does not get any notifications. This is completely invisible. So this is the kind of mistakes that happen when you're doing dependency management. So you don't have to just consider the versioning schemes that you're using for the project, but also the dependencies that you built in when you distribute your software. And then there are cases where it's more extreme, where it's hard to believe that it's by accident, where all of the version information is just stripped out. You have nothing. So this is like the least useful that you can have. The only thing you get is a list of package, and well, good luck. Try it, so don't be there, like obviously, but my call to action to everyone is to really work on the previous example, the holes that we create in our dependency chain, where we are depriving the users of our software of very valuable information. So it is our responsibility as open source producer to give all the information that we have about security to their users, and that starts with version. Thank you. Any questions?
How does the kind of container level, how do you generically identify packages that are going to build into an image with all the layers that get pulled from main number, start places, and you scan everything in SBIN or whatever? How do you gather that?
So the question is, how do you get this information when it's been compiled? And this is not something this industry is doing particularly well. Luckily, Golang is done for us, but in ecosystem where this is not the case, what I've been trying to do with open source project is to create a custom SBOM that is exported at the same time as it's released, that says the compiled includes all of these, because you don't necessarily want to distribute the package file, the package manager file. So the SBOM is a more generic way of doing this. It's a more standardized that works across ecosystem, and that's a very useful way to deal with this problem. And if you're using Docker Scout, it'll automatically pick it up and embed it in the bigger picture.
So Scout will, it might see the app packages if this is a Debian-based thing, and will list those, whether or not it digs into a Python apps requirements file or something. It's a different matter.
That will depend on the application. Like scripting language generally is not as much of a problem. And then when it comes to Debian world, you get whatever Debian ships. So, but when we are including application that falls outside the package manager of the OS, this is where we have more opportunity to create even more rich data to help our users.
So have custom like bomb compilers for each framework language to be like, oh, this is a Ruby on Rails app running in Docker, run that one. This is a Python.
No. So it's not a custom BOM scanner for each. It's the same BOM. It's just one runs at this level, and then the same one is able to propagate as you distribute and download it. So it's not a custom thing. I am a contributor to SIFT, and that's a big part of what we're doing is getting package detected properly, getting new ecosystem detected in your ASBOM. So it's not a custom thing for everything. We do a tool that works well across the board.
Check out SIFT.
Thank you.